This is the evaluation section, the fourth section of your design coursework, and it's worth 6 marks. It's got 4 sections. Explanation of how the system works. This is new compared to the assembly coursework. And the last 3, comparison of spec, overall performance evaluation, suggestions for improvement, are all the same. They will be slightly longer because this one is longer, but really they're all the same. So let's start with the new thing. This will take up about a page. And this new thing is worth 3 marks for this one page. So it's quite important to get this one page right. This kind of gets rushed by a lot of students who end up getting either the bottom band, so 1 mark, or sometimes the middle band, 2 marks out of 3, when really it's not too difficult to get 3 out of 3. So let's just focus in and get those marks. The rest has pretty near identical mark scheme to the assembly coursework. The only difference is it says 3 suggestions. Oh, it says thorough, but really if you write them all in the assembly, it's no different instead of 2. But this top one is worth 3 marks in and of itself. So let's talk about that and how to get that right. And you'll notice at the bottom it says there is a sustained line of reasoning which is coherent, substantiated, and logically structured. The information included in the response is relevant to the argument. So the exam boards have to include a section where they also check the quality of your writing. So have you got spelling mistakes? Can you write coherently? Does it make sense? I don't think you should worry about this. So sometimes people get a little bit worried about this. Don't get too concerned. If you are writing good electronics, then your writing will be good. If you are writing bad, unclear because you don't know what you're talking about, then it won't be sustained, coherent, substantiated, and logical, or however you want to write it. So don't get too head up on that bit. So, explanation of how the system works is very much an engineer's view. So you're writing for a specialist. You should be able to give this to someone else in your class. They should be able to get it without any problem. This should go block by block on the block diagram and explaining how the signal passes from one block to the next without missing any out and without kind of jumping. The person reading this, you can assume, will know what a 555 astable circuit is and how it works. You can assume that they know what Schmidt trigger is and how that works, or a comparator, or an AND gate. You do not have to explain what's going on in an RC monostable when the capacitor is charging and then it's triggering the NOT gate. You can just say the RC monostable was triggered from this previous subsystem, which will cause the NOT gate, will cause the RC monostable to output high for 10 seconds. That's it. You don't need to go into resistor or capacitor values. They know what they're talking about. Do make sure it's clear and coherent, as it's easy for this to get quite messy. The more complicated the circuit, the harder it is to keep it clear. So bear that in mind. Do make sure that it's really, really clear. I would recommend that you get a classmate to read it to see if it's clear and coherent. This is not something that you can give to your family or your friends. Like the user guide at the end of the previous section, that was something that you could have given to a friend who doesn't do electronics, and they should have been able to use it. This is something that you need to give to a classmate, someone who knows stuff. This is, sorry, it's a little bit blurry. This is just a decent example. So I'm just going to talk through it a little bit and sort of talk about why it does such a good job. You're welcome to pause the video, obviously, and have a look at a bit more detail on it. This is... So if the temperature rises above 35 degrees centigrade, you can see they're being precise here. The potential divider for the fan outputs a higher voltage than the inverting input of the Schmidt trigger. The inverting input is kept constant by using a pot at a set value. Schmidt trigger outputs logic 1 because the non-inverting input is higher than the inverting input. There you go. So this is already two subsystem covered. This voltage is then sent to an AND gate. The other input of the AND gate for the fan is 555 monostable connected to a toggle. When the button of the monostable is pressed, logic 1 is outputted for etc., etc., etc. So this will take up about a page. You do need a lot of detail. Do have a look at some of the exemplars. Just look at your block diagram and explain the signal transfer between the different blocks. That's really, really important here. Yeah, so it works in terms of function of each block and the signal transfer between blocks. So that's really, really important. Okay, the rest of this is stuff that you've already seen in the assembly coursework. I will go through it again. If you want perhaps a little bit more detail, do look back through the assembly coursework video because there's a little bit more detail there. So comparison of the spec, you're going to list the spec again, make sure that everything is in the original spec and testing section. It should be the backbone of your work. Nothing should be missing or extra in any one of them. Evaluate whether it meets the spec. So, you know, how well is it meeting that spec point? Is it easy for a user? Is it difficult for a user to do, to use? Is it saving power from a low voltage, etc.? A couple of examples here. I'm not going to go through them now, but do pause the video if you'd like to have a look at those. Overall performance evaluation. How well does your circuit work for its intended function? That's really the question that you are asking yourself. So this should be drawing together the points on the spec. You don't need to state if it meets those points, but you should be mentioning anything that doesn't meet and whether that really affects the overall performance. So if the alarm doesn't go off when the button's pressed, then that's a big deal. That's kind of a massive problem. On the other hand, if the voltage was supposed to be 6 volts and you end up getting 7 volts, and the PIC chip gets a bit hot, but it doesn't stop functioning, then you would be stating that it's not meeting the spec. The PIC chip is getting a bit hot, so it may affect whether this system could run for a long time because it may overheat. But in the time period that you've run it, it does still function. So you think it's context. It's very much context. Like, what is the purpose? Is it affecting it? You should also discuss the limitations of your circuit. This is where you get into the critical top end marks, and this will lead into suggestions for improvement. It's a good idea to put down a limitation that you write a suggestion for improvement for, but you don't have to. But it makes a better flow. And remember, you are being graded on the quality of your writing. So if everything flows, then it's easy to say that it's coherent and sustained logical argument. Suggestions for improvement. The mark scheme does say only your best 3, so do 4. So yeah, it says the best 3 thorough ones. I would say always do 4. Always give yourself a spare, just in case one of the ones you wrote was just not that great. You need to say again why and how. So why will it improve the circuit, and how are we going to do it? So here's one example. The counter will be improved by adding another one, so we can go to higher scores. So this is the what, which is kind of obvious. Like, what are we doing? This next bit is the why. And this is the how. How on earth are we going to do that? So what, why, how. You don't have to do it in that order. You can do what, then how you're going to do it, and finish with why you want to do it. Up to you. I think this order is probably the one that makes the most sense to me. You can see I'm talking detail here. I'm talking chips. I'm talking how they'll feed into the system, how they're going to get triggered. It's the second example here. So quite a few people end up with systems where something like, because you've got an analog component, something like heat or light goes too low or too high, or it triggers something, but they generally have something that is only triggered when it goes too high or only when it goes too low. So an obvious improvement would be to cover the other thing, because usually you want your particular temperature to be within a nice range. Yeah, if it gets too hot, that could be a danger, but also if it gets too cold. So talking about that is kind of an obvious one. And again, yeah, the what and the why are all kind of together there, and the second part is the how. And that's it.